everyone, this is Abdul from Pythonist. Every operation you are going to perform on your computer ultimately have to transform them into mathematical operations. So what's the optimized way to process numbers for mathematical operations? And what's the role of matrix and vector computations in this context? Let's try to explore in this video. Regardless of what problem you're trying to solve on your computer, you will encounter vector computation at some point. Vector calculations are integral to how a computer works and how it tries to speed up runtimes of programs down at the silicon level. The only thing the computer knows how to do is operate on numbers, and knowing how to do several of those calculations at once will speed up your program. So in this video, I'll try to unwrap some of the complexities of this problem by focusing on vectors and matrix implementation using pure Python. And we will understand how NumPy can rescue us from these worst situations. So let's try by getting introduced with vectors and matrix. A vector is a tuple of one or more values called scalar. Another more detailed definition of vectors as vectors are built from components, which are ordinary numbers. You can think of a vector as a list of numbers and vectors algebra as operations performed on the numbers in the list. I have taken this definition from the book No Bullshit Guide to Linear Algebra. Vectors are often represented using lowercase characters such as v. For example, v equal to v1, v2, and v3 is a vector where v1, v2, and v3 are scalar values. Vectors can be introduced using a geometric analogy, where we have magnitude and directions on the vector space. So for example, we have a vector A as 3 and 4 in the diagram. The magnitude of a vector can be denoted by this notation, which is actually the square root of the squares of both values. So it will be the square root of 3 square plus 4 square, which will become 5. So let's write a very simple vector using Python. You can utilize VPython, which is Visualize Python, because vector is not a built-in type in Python. So you have to install the VPython module on your system, or you can utilize any online environment. I'm going to utilize the Truncate Glow script environment. I'll post the link below in the description. If you want to utilize this environment, go into the description and hit the link there. So here you can see that I'm inside the Glow script environment on Truncate. So let's define a very simple vector as v. So I will say v equal to vector. I can call this function because the Glow script has this built-in variable vector. So we can directly call this function vector and pass some numbers like 2, 5, and 7. Then let's define another vector as b equal to vector 3, 2, and 5. Let's print out the result of v plus b, as you can see the result here. We can perform various and different kind of operations and vectors like multiplication, additions, subtractions, etc. But this is not the scope of this video. So this was the very short introduction to the vectors. Let's try to explore the matrix. A matrix is the two-dimensional data structure where numbers are arranged into rows and columns. For example, we have this simple matrix you can see here. This is a 3 by 4 matrix because this matrix has 3 rows and 4 columns. Python doesn't have a built-in type for matrix. However, we can treat list of lists as matrix. So for example, I have a list A which holds a multiple list inside that. And if we represent this list in the form of a matrix, we can see that this matrix has 2 rows and 3 columns. So let's try to write some code to understand the matrix. So let me define a matrix A equal to which holds 3 different lists with the 4 columns in each list. So this will become the 3 by 4 matrix. We can look up the values from these lists by using the list conventions here. So I will simply say print A and just pass this A, so you can see that actually it will just print out the entire list with all of the nested lists. Another way is actually that if I just want to print the second row of this matrix, what I can say, I will simply print A into 1. It will print out the second row of this matrix. And if we want to get the third element of the second row, I'll simply say A into 1 into 2. So it will simply print out the third element of the second row. So this is how we can get an element and a row. But what's about the column? If you want to grab a column from this matrix, we have to write a for loop. So first I'll define a variable call. Then I will just simply write a for loop as for row in A, then call that append row into 2 because we are just trying to get the third column. So it will be at the index of 2. So in this way, we will be able to grab the column of this matrix. Okay, that's a very concise introduction to matrix. But why do they matter? If we talk in the context of artificial intelligence, machine learning, and data science, it's very important to understand matrix primarily because when dealing with a lot of data, the computations can be greatly optimized using matrices. If you do it right outside of these fields, computers can do math with matrices a lot faster than if you were to multiply if using single variables. Matrices also playing a huge role in graphics. Any image is a matrix and each digit represents the intensity of a certain color at a certain grid point. Okay, let's talk about an important problem we have to take here while working these kind of computational problems. It is memory fragmentation. Python doesn't natively support factorization. There are two reasons for this. Python list store pointers to the actual data, and Python bytecode is not optimized for factorization. So for loops cannot predict when using factorization would be beneficial. The fact that Python lists store pointers means that instead of actually holding the data we care about, lists store locations where the data can be found. For most users, this is good because it allows us to store whatever type of data we like inside of a list. However, when it comes to vector and matrix operations, this is a source of a lot of performance degradation. The degradation occurs because every time we want to fetch an element from the grid matrix, we must do multiple lookups. For example, doing grid into 5 into 2 requires us to first do a list lookup for index 5 on the list grid. This will return a pointer to where the data at the location is stored. Then we need to do another list lookup on this returned object for the element at index 2. Once we have this reference, we have the location where the actual data is stored. The overhead for one such lookup is not big and can be in the most cases degraded. However, if the data we wanted was located in one contiguous block in memory, we could move all of the data in one operation instead of needing two operations for each element. This is one of the major points with data fragmentation. When your data is fragmented, you must move each piece over individually instead of moving the entire block over. This means you're invoking more memory transfer overhead, and you're forcing the CPU to wait while data is being transferred. There's a different solution has been proposed to this problem like Paroff, but these topics are not the scope of this video. So I think that's enough for this video. We have explored vectors and matrix and the main problem while performing complex mathematical computations. In the next video, I will expose an amazing library which can help us to optimize these computations. So let's see what this library will bring for us in the next video. So if you like this video, be sure to subscribe to my channel and hit the bell icon so you will never miss any fantastic video in the future. Thanks for watching.